right, so tonight we're going to talk about climate change in geologic history. And the way the talk's going to go tonight is first I'm going to go over some background, so what changes climate, and then we'll go through the early Earth. This is baby Earth. This is like 3 billion-year-old Earth. And we'll talk about the Great Oxygenation Event, the Boring Billion, and what I like to call the Manic Millions. Then we'll get into Middle Earth, which is basically the Paleozoic and Mesozoic, and it's the time of death. So I'm going to talk about the Great Dying and the Kpg Extinction Event. Then we'll get into our present Earth. This is basically the past 66 million years, and talk about the Paleocene, Eocene thermal maximum, Cenozoic cooling, and then our current situation. And then we'll have fun thinking about future Earth. So let's get started. What causes climate to change? Well, one thing that can cause climate to change is our solar output. Now, when we think about solar output on our human timescale or even thousands of year timescale, it's negligible. It's nothing. It's hardly anything. You can see here, this is billions of years since the origin of our solar system and Earth. So this would be 0, the formation of the Earth. Here we are at 4.5 billion years later. So you can see how much that has changed over 4 billion years. And it will continue to change until we get to the red giant phase, and then Earth will be destroyed by the sun. So we don't have to worry about it past 10 billion years from now. But anyways, basically what I want to say is I know solar output is sometimes brought up with climate deniers, and while no, it doesn't make a huge difference in our own human lifetimes, when we look at geologic time over the whole thing of it, it can make a pretty big difference. And right now with our solar output, we are doing about 8% of our solar output every billion years. So it's still pretty small, only 8% over billions of years, over a billion years. So that's one thing that has a little bit of effect on climate. One of the major things, though, that has effect on our climate is these things called the Malenkovic Cycles. And it's basically the change and wobble and tilt of our planet as it orbits the sun. And any of that that changes can change how climate happens on our planet. So we have precession, that's the wobble, where our North Pole is pointed. You have obliquity, that's where true north is, so comparison to like how far our North Pole is actually off of North Pole, so we very rarely are hitting right at it. And then there's eccentricity, and that's the shape of our orbit. So sometimes it's more oval, and then sometimes it's more circular, and that can change how close parts of our Earth are at certain parts of the season, at certain parts of the year. All three of these things working together or separately can have massive effects on our climate. And they seem to go in these cycles. Each one of them has a bit of a cycle, a 26,000-year cycle, a 41,000-year cycle, and a 100,000-year cycle. And we can at least trace this one back in the rock record to about 215 million years. So we know for at least a quarter of a billion years, eccentricity has been working on our climate. Figuring out what changes the dominant one that affects the most is kind of unknown. We'll talk about these two a little bit more when we get into the ice ages later, but basically for a really long time we're real steady in this 41,000-year cycle, and then all of a sudden it switches to a 100,000-year cycle. And that's actually a big question, is why did it do that? And we don't know. That's for you guys to figure out someday, I guess. Plate tectonics. Let me get this thing going a little faster. This is a pretty slow video. So plate tectonics is the theory of how our major landforms came to be and how they move around. So most of you know, especially if you've been in any of my other talks, you'll know that plates change around a lot. And so this is kind of the blood, sweat, and tears of geology over the course of 200 years, figuring out where all these things go together. So we're in the Pennsylvanian now, we're in the very late Paleozoic and the Permian. Here's Pangea forming. Boom, here we have Pangea. Now it's starting to split apart in the Triassic. The Jurassic, we got dinosaurs right now, and then into the Cretaceous, and you can see the Western Interior Seaway forming and disappearing, and then boom, dinosaurs are dead. We're into the Cenozoic, here's our ice sheet, and then boom, the last ice age. So things have changed a lot. And depending on where the continents are, how they're moving and what they're doing can change and affect our climate. And it does this in 3 major ways. One of them is polar land masses. So just like today, Antarctica is stuck on the South Pole and it's got an ice cap. Well, we tend to see that throughout Earth history. Whenever land masses get isolated on the poles, glaciers tend to grow. Also, you have a control of CO2 via seafloor spreading. So as the seafloor is creating more seafloor, it's splitting apart. There's a ton of volcanic activity happening. When that is rapidly changing, there's a ton of CO2 going into the atmosphere. It can create a warming climate. When it's slow spreading, you have low CO2 going into the atmosphere. So that's one other way it can control. And then the other way is by uplift and erosion. So anytime you have high erosion, you can actually pull CO2 out of the atmosphere. So we can see every once in a while, after major mountain building events, you have a cooling episode from all of that erosion that's happening. So plate tectonics and the Malenkovic cycles are probably the 2 biggest controls and trigger to climate change, but there's definitely one other one, and it's life. So it's easiest to see in plants. This is an Eons episode if you're unfamiliar. I host a YouTube channel called PBS Eons, and we talk about the history of life on Earth. And this is one of our episodes, and it's how plants caused the first mass extinction event. So as for the very first little plants move onto land, they change the ecosystems drastically, and we think that the Ordovician extinction event, at least the first part of it, was driven by plants. This happens again at the end of the Devonian. We have another mass extinction event at the end of the Devonian, and what is right up against that mass extinction is the first forests. So plants went from just being like the little scuzz around the edges of the rock to being widespread, huge forests. That is another. So plants are photosynthesizers. Remember, they're taking in CO2 and they're breathing out oxygen. And so they're pulling CO2 out of the atmosphere. And so when you go from no plants to some plants, that's going to change it. And then when you go from some plants to a lot of plants, that's going to change it as well. So it's easiest to see in plants, but of course, then there's also us. We are life. We are part of our system, and we have changed it quite drastically in our very short history. So now all of these things work together into feedback cycles. So over here are the 2 main ways of you kind of have a checks and balances system. So you have some type of trigger. So in this example, it's seafloor spreading. So you have fast seafloor spreading, you get a ton of CO2, that warms the climate, that increases erosion, which decreases CO2, which causes reduced warming. So this is how it gets hot and then it gets cold. So usually it doesn't get to extremes very often. There's a nice pendulum that swings us back and forth. This is a negative feedback system. So we have slow seafloor spreading, we have slow CO2 output, we get into an ice house climate. This decreases chemical weathering, and that decreases that CO2 removal, and so CO2 goes back up, and that reduces the cooling. Now, every once in a while, these cycles can get caught in their respective ice house, warm house environments, hot house environments. And these are runaway feedback cycles. So you have some type of initial change that causes some type of climate warming, and that climate warming does something else that increases the climate warming, that increases the climate warming, that increases the climate warming. And you get into these feedbacks. Now, what stops them when it gets extreme is usually something like this. Maybe it's a change in the tilt. Maybe it could be seafloor spreading basically coming to an end. Maybe it's some big ice sheet that covers the planet. We'll talk about a lot of different ways. Anyways, but at some point they will break. That cycle will stop and it'll switch back. But feedbacks are very, very important because a lot of times one change will lead to another, and then you have a cascade of changes through your climate. So what does this mean? This means that our atmosphere has changed a lot over time. So this starts about at 4.5 billion years ago. So this is baby Earth. It starts right here. And you can see we're not 100% sure what the very, very first atmosphere is, but soon after that, we have a CO2-dominated atmosphere. We have this little methane fart right here, and then boom, oxygen comes up. And we're going to talk about this oxygen spike here in just a second. But this is basically just to show you how we've gone from a CO2-dominated environment and atmosphere to a oxygen-based atmosphere over the course of 4 billion years. So obviously the resolution is pretty wide on this, but it gives you an idea of how much change has happened over the course of our Earth's history. The other thing that has happened is our temperature has swung widely over the years. So this starts at 500,000 or 500 million years ago. So basically with the start of the Paleozoic. So you can see we were real hot. And any time in the red here is a time without any ice. There's no ice. Maybe some minor little alpine like this, you know, but no major ice sheets. Below this line, you do have polar ice caps. So there's been many, many times on our planet's history, just in the last 500 million years, that we've had 0 polar ice caps. No big glaciers at the poles. And what's fun is not on this graph, but we also have times where our entire planet has been coated in ice. So we have 2 extremes that our planet has gone through several times, from completely ice-free to completely coated in ice and everything in between. Now, a lot of times these temperature drops and or spikes are related to mass extinction events. So these are the 5 major mass extinction events, and you can see a couple of them pair quite nicely with some huge temperature swings. We'll talk about this one, and we'll talk about this one. So let's get into early Earth. All right. So here we are at Earth about 3 billion years ago. If you were looking at Earth from space, you might not actually be able to see the surface. It might be a little bit more like Venus, only for a different reason. So it might have looked a little pale orange because of all of this haze that was produced by microorganisms and things like that. Now, if we got all that cloud out of the way, Earth would look way different though. The land masses were probably magnesium rich and they would have looked orange. The oceans were absolutely full of free iron. They were just, iron was everywhere. And so our oceans would have looked green. So it was a very different time period. It was very hot. Atmospheric pressure was crushing. About 4 billion years ago, our atmospheric pressure was 215 times what it is now. That means that water wouldn't boil even at 450 degrees Fahrenheit. It was weird. This is weird times. But anyways, 0 oxygen. No oxygen during this time. Yep. We'll talk about that right meow. Right meow, actually. So the Great Oxygenation Event. All right, so this occurred about 2.5 billion years ago. We see it in the rock record worldwide. It's a really nice index. And it happened because of 2 things. Life, photosynthesizing microbes. So like cyanobacteria, stromatolites, they're pumping out oxygen. And eventually, it built up enough that it starts to react with all that iron. The iron in the air, the iron in the sediment, the iron in the rock, the iron in the bottom of the ocean, the iron in the water, and it started to react with it. So what happens when oxygen meets iron? Oxidation, and it rusts, right? So basically we have a worldwide rusting event that occurs. We also have plate tectonics that's happening. So at this point, we have these big basins. We've had some rifting going on. We have these brand new shallow basins that are just bearing a ton of organic material, including carbon. So this is a big carbon sink here too. So not only do we have CO2 sinking into life, we also have CO2 sinking into the rock as well. So that pulls out all that CO2 and allows oxygen to raise up to an astounding 1%. But it did all sorts of stuff at 1%. I mean, nothing to 1%, that's a big jump. That's a 100% increase, right? Right? So we get banded iron formations, we get red beds. So these are our rusting. This is our terrestrial rusting. This is our ocean rusting here. We get an ozone, well, a whiff of an ozone layer. Ozone is forming. It's still like you would die from UV radiation, but we're getting there. We're getting there. And then we also removed pyrite. So I always thought that this was real fun. So pyrite, fool's gold, it's very reactive. It does not hang out for a very long time on the surface of our planet. But when there's no oxygen to react with it, it just hangs out. Can you imagine beaches of pyrite riverbeds full of sparkling pyrite. As far as the eye can see, you wouldn't be able to breathe to enjoy it, but you could see it. But once oxygen started to build up, all that pyrite started to be removed from the system, all because oxygen went up to 1%. This might be what it would have looked like by then. I think that the water probably would have been like this weird transition. So all of these little bumps and lumps here, those are stromatolites. They are a type of cyanobacteria that grows in these little mounds. I'll show you some pictures in just a second. But this is what's photosynthesizing. We don't know if they had chlorophyll yet, so I can't tell you what color they were. They were probably like a darker color or tan or something like that, like modern ones are. And then the oceans would still be green, but as you got closer to the life and all of that iron is rusting, it actually doesn't turn it red. It pulls it out of the system completely, and so we're starting to get blue water. So it would have been a little bit of a transition. But you still would have had a bunch of volcanoes going off. The atmosphere would have been CO2 rich. You would have had 1% oxygen. But all of the life at this time that you could see, at least, are these stromatolites, these algal mounds. So this is what they look like today, which is absolutely amazing that they've lasted this long. The oldest stromatolites that we know of are about 3.5 billion years old, and we still have them today. They live in very, very specific types of environments. This is Shark Bay in Australia. If you ever get a chance to make the journey to see these things, it's pretty amazing. This is a hypersaline environment. That's why they're still alive. There's nothing else that can live in it and eat them. Yeah? Yeah. Yep, so actually the only living part of this whole thing is about a millimeter crust around the top. The rest of it is this pedestal that it has built up over time using sediment and sand grains that wash in. So this is right at a tidal zone. And so as the water comes in, it brings sediment with it. And this cyanobacteria is sticky. And so the sand grains get caught in it. It's sticky. And they're like, oh, wait, I need the light because I'm a photosynthesizer. And so they grow on top of it. And then they do that again. And it's achingly slow. I mean, millimeters per millions of years. It's very slow growth. But that's what was happening. Basically, for a whole billion to 2 billion years, this was it. This was our life on planet Earth. It was just a whole bunch of stromatolites pumping out oxygen. So the oxygen that we breathe today, we really have to thank to these little guys right here. Now, if you want to see fossils of some stromatolites, you can go up to Grinnell Glacier and the hike to Grinnell Glacier in Glacier National Park. You actually walk across the surface of stromatolites. So this is basically like if we could go and slice off the top of all those modern ones, that's what you're looking at here, the eroded surface. Each one of these big round things would have been one of those pedestals. And on the very, very top, the little crusty top, there would have been tiny little cyanobacteria growing and photosynthesizing. These ones here are a little younger. They're only about 1.5 billion years old, only. I mentioned banded iron formations. This is what they look like in situ. So if you went out to look for banded iron formations, this is what they kind of look like. So you can see these red lines going up through it. But the fantastic part is when you cut and polish it. Ooh, you can barely see that. Well, take my word for it that this is absolutely gorgeous, and it's a bunch of bands of black and red, and that would have been the sediments that were different amounts of oxidation during the Great Oxygenation Event. So now let's move into the boring billion. It gets a bad rep. So about 1.8 billion to 800 million years ago, this is actually a time of pretty much stasis. We were kind of just chill. No major things happened. No evolutionary breakthroughs happened at this time. We do have some tectonic activity, but these continents are very, very small, and the difference between Nuna and Rodinia is pretty small. It's like they kind of just separated and then they came all back together. So it was not a big change. You do, however, see this drop in oxygen. So we went up to 1%, and then we came down to less than 1%, actually a lot less than 1%. So we had really low oxygen again. We think we had hydrogen sulfide bacteria going crazy in our oceans, so it's just increasing hydrogen sulfide. There's just sulfur everywhere. I've heard this called the worst smelling time in our planet's history. So it was basically like the air everywhere on our entire planet smelled like rotten eggs for 1 billion years. But this is an example of stasis. You're going to see a lot of wild changes in climate today, and this is one of the times that seems that not a lot happened. It was kind of capped by these two supercontinents. It's also capped by a couple of glaciations. It's capped by some big evolutionary advances, but really nothing else happens in the boring billion. Most of the minerals that we use today were formed during the boring billion, so yay for that. But otherwise, it's a pretty chill time. Pretty chill time. Stinky, but chill. Now we get into the manic millions, and during this time, we switch from extremes several times. We go from snowball, slush ball Earths to hot houses to slush ball to hot house to slush ball, and we do that, the Earth goes through that in about 200 million years-ish. It goes through that cycle about 3 or 4 times, going from absolute extreme to absolute extreme. So you get this extended cold spell for whatever trigger that I've talked about today. For whatever reason, it starts getting colder. And your oceans start to freeze, and your polar ice caps grow, and then all of a sudden it gets extreme because you get all this lowered reflectivity. It causes further cooling, and then you're left with this snowball Earth. And some people call it slush ball because they think that this might have been just slushy ice in the middle and not completely sealed solid in a coating of ice, and that's probably what it was. But during this whole time, you can see here, we have volcanic off-gassing. Glaciers don't just shut off plate tectonics all of a sudden. So you still have seafloor spreading, you still have volcanoes going off, you still have CO2 building up in your environment. And at some point in time, it tips the scale, and it goes crazy the other way. You start to get these big giant melts that start kind of in the middle, and then they go to the poles. And you get a positive runaway feedback cycle that goes in, and then that feedback cycle starts all over again, and then you're here. So here's kind of what it looked like. This one here at 716 million years ago is called the Suttonian. Let me see, boring manic millions. Yeah. Stuartian glaciation, and it is the longest and most severe known glaciation in recorded history. This was a big one. The first one was the worst. They get periodically less worse as it swings. So you can also see how the plates have changed a little bit over time. This one only shows 2 of the 3 or 4 of the glaciations, but this one was big. Now, what did life do? Well, some of it was cold adapted and was like, hey, yay for me, I was already cold adapted, this is great. Others hung out in these little areas of refugia, we think. So areas that were less frozen or possibly not frozen at all around the equator is where life hung on and got ready to go just bananas here in just a minute. So in the Middle Earth section, this is where we kick off really with life. This is probably the last 500 million years or so. It starts in the Cambrian. And specifically, this is the time where we get a lot of life. But when you have a lot of life, you also can create a lot of death. So that's what I'm going to talk about, some death. So the big 5 mass extinctions take place during this time, what I'm calling Middle Earth here. We have the Ordovician extinction event 440 million years ago. 85% of life went extinct. And this was a major cooling followed by a rapid warming event. And this first cooling was probably triggered by plant life. The Devonian, 359, 75% go extinct. Glaciation caused by new forests, lowered the sea level. Everything goes. The Permian, was a bad one. 252 million years ago, 95% of life goes extinct. This is the closest our planet has ever been to just wiping it all out. And this was massive volcanic eruptions were causing extreme global warming during this time. The Triassic was pretty similar, 201 million years ago, and 80% go extinct. And this is Pangea splitting apart, and you got all these volcanic eruptions, and it was really bad. The Triassic was bounded by 2 mass extinction events. It's just don't go to the Triassic. And then you have the Cretaceous extinction event, 66 million years ago, 76% of life goes extinct, and this is when the giant space rock impacts our planet, and there's also some large volcanic eruptions, which we'll talk about. So all the non-avian dinosaurs are kaput at this point in time. So I'm going to talk about these 2 in particular. The first one is the Great Dying, and this is the largest mass extinction that we have record for, and it's pretty bad. It was a really bad time. In Siberia, you had these massive lava spews. It's not like an eruption, it's just like an upwelling of lava for millions of years. And it covers about 1 million square miles, and in some places it was 2.5 miles thick. That's a lot of lava. These eruptions obviously were releasing trillions of tons of carbon dioxide and other greenhouse gases. We think that temps on land reached a sweltering 140 degrees Fahrenheit. And if your land is that hot, that means your oceans are about hot spring hot, about 104 degrees Fahrenheit. You had acid rain, it killed forests, there were forest fires, you had these nasty algal blooms that killed anything that ate it, touched it, breathed it. There was just a real bad time. And this is probably a prime example of what happens when a positive feedback cycle goes wrong, is the Permian extinction event. I mean, it just was a cascading disaster of death for quite a long time. But not as long as you think. We think that this whole thing, all of this death, all this horribleness happened in about 120,000 years. In the grand scheme of things, that is not a very long time for 95% of life to go extinct. So that's the Great Dying. So again, this is definitely climate driven, and it's the #1 trigger is volcanic eruption and spewing all that CO2 into the atmosphere. Now the KPG, I love this figure. It was either this or a bunch of T-Rexes just like screaming at a flaming ball coming in, and I thought this one was way more fun because it gets the point across about what actually caused the extinction event. It wasn't the asteroid. I mean, it was, but it wasn't. So we've had a lot of big space rocks hit our planet before, and none of them have been associated with a mass extinction event. This one is like, right, it's yes. Yes, it did cause it, but for a different reason than you may think. So when this thing hit the planet, it was like 100 million, yes, that is 100 million megatons of TNT going off. And you can see it comes incredibly close, actually, to hitting our mantle. So the hole that it drove down into our planet when it hit ejected a lot of stuff, right? So whenever that impact happens, it moves all of this stuff out of the way, including a lot of the meteorite itself. Now, the meteorite was about 7 miles wide, and it was larger than Mount Everest. So Mount Everest being flung across space and slamming into our planet. And it's popped off in the Yucatan Peninsula. And you can actually go there, and they've got a little monument to the Chicxulub impact. It's amazing. I will go there someday. I have not been there. The material that was ejected surrounded the globe in about an hour. And then everything that was left, the small sooty stuff, blocked out the sun. This is the ultimate killer of the dinosaurs. So what that did was basically have a massive food chain breakdown. So what happens if you block out the light? This is called an impact winter. So what happens? Kills the plants. All your photosynthesizers are like, who turned off the lights? And we actually see massive plant extinctions. Basically, all the plants that you see today came from a few survivors from the Kpg impact. So the plants go extinct, but not only just the land plants, anything that photosynthesizes in the ocean. And I hope y'all know, but plankton, and a lot of it photosynthesizes, is the base of the food chain in the ocean. So you take out the base of the food chain, and there's just a cascade effect from there. So if you're a massive herbivore that weighs over 10 to 50 tons, and you got to eat 1,000 pounds of vegetation every single day, and all of a sudden your forests are gone, that's a bad day for you, right? And if you're T-Rex here that does not have bunny arms like this shows, and you need to eat 500 pounds of food a day, and all of your big plant eaters are dead, you're also dead. So what we see actually is kind of a bias, extinction bias based on that food chain breakdown. You have the plants go, you got the herbivores go, you got the carnivores go, and you got basically anything that was big and that couldn't run and hide, because anything within 1,000 miles of this impact was incinerated. So that was also a really bad time too. So the things that survived were pretty small. After this extinction event, the largest thing on our planet was about the size of an alligator, like an average size alligator, not like Sarcosuchus or something from the Paleocene later. So about the size of an alligator. Omnivores, insectivores, scavengers were having a heyday because of all the dead stuff. And small things, birds that could eat seeds and nuts instead of flowers and things like that because things weren't blooming because all the plants are dead. Small things like mammals could make it through. We can hide, we can burrow. So a lot of small things and generalists made it through this extinction event. But really, the climate change was due to the soot from the impact. A few years. So it would have probably created a pretty tough year or two for terrestrial extinction, but there would have been a lag in the oceans. So we actually see ammonites. The last ammonites disappear at the very beginning of the Cenozoic, actually. They technically make it through the extinction event, but we call them a dead clade walking. They were not healthy enough to go on from there. It was just a slow death. Yep, there was still oxygen, things like that, but it was that major food chain breakdown. So although they could breathe, they had nothing to eat. Yep. So here's an example of extraterrestrial climate change. All right, let's talk about our present Earth. So again, this is basically 65, 66 million years to present. So here we are, we leave off the Cretaceous as a hothouse world. It is very warm in the Cretaceous, and you can see that. We are here, this is today. Well, actually, we're up here now. So you can see, we were coming from a hothouse planet. We don't think there were any glacial ice sheets, definitely not ice sheets, but probably not even any glaciers in the Cretaceous. So it starts off pretty warm, and then all of a sudden we have this crazy peak right here, the PETM. And then the Eocene, early Eocene climatic optimum, yes. And then right there, though, that's kind of the end of our hothouse world. And it starts to decline. Then we get the Antarctica glaciation, we got some spikies here, and then we get this rapid glacial cycle, which is our last, most recent ice age. So I'm going to hit a couple of these, a few of these. I'm going to talk about the PETM, and then we'll talk about the Cenozoic cooling, and then we'll get into our most recent ice age. So the PETM is called a hyperthermal. So you can see that climate was already going, I mean, it was getting hotter right here, and then there's this massive spike, and there's a couple of extra ones. But this one, the PETM, is a really, really, really bad one. And look at this time scale. This one, so that's 10 million years. So you can see this happened in like 200,000 years. This whole thing is, 200,000 years. Crazy spike in temperature. So going from like an average of like a little over 10 to almost 13 degrees Celsius, average temperature in the oceans. Now, we're not 100% sure what caused these little hyperthermals. We think that there was some type of big CO2 event, but we're not 100% sure what caused this big spike right here. We know that CO2 goes up. We know it goes up. But we're not exactly sure what the actual trigger is. But what's scary about this little PETM is that this is the most well-known climate change event in our Earth's history because it happened so recently. The other thing is that it's the closest proxy to what's happening right now. But this, even though this looks like almost a vertical spike, is nothing compared to what we're doing right now. So what happened in the ocean when it got that hot? We get a really, really hot ocean, and we also get a very acidic ocean. So we actually have a mass extinction of a lot of microorganisms in the ocean. It just wasn't big enough to be like a big five. On land, what we see is mostly animal migrations. Animals just moved out of areas where it was uncomfortable. So you had northward or southward moving species, but they just kind of moved around. This is Champsosaur. This is one of these dead clade walkings from the Kpg event. They go extinct shortly after this picture was taken. So let's see. This is, I think this is the Bighorn. Yes, this is the Bighorn Basin in Wyoming. So we have these big spruces. We have turtles, crocodile things in Wyoming. So you can already tell it's a much warmer period of time. And this would have been about 58 million years ago, and the annual average temperature was 68 degrees Fahrenheit. Today, it's 45 degrees Fahrenheit. So again, this is before the PETM, so we're already a much warmer climate. In the middle, right here, is the 56 million year PETM. It happened 56 million years ago. At this point, the average temperature goes up to 77 degrees Fahrenheit. That's like a 10 degrees on average Fahrenheit change. Our redwoods shifted north. We had palms move in, all sorts of animals changing. We've got a much different environment. You see, look all this water, and we have equisetum, horsetail, and then it's just like dry savanna, right? Over here is afterwards, about 55 million years ago. And the average temperature cools back down to 68 degrees Fahrenheit, but we have changed back to our Paleocene environment, but we just have a few different players in the game now. So some of the animals that moved out didn't move back in, and some of the animals that moved in took over. So even though we're back at the same climate, our animals are slightly different, but there were no major large mass extinctions during this peak, which maybe that's some hope for us, but I don't know. This talk is relatively heartbreaking. You'll see. So again, we get a major change, this cooling. Did I skip a slide? Yes, I did. All right, so after this hothouse world, and I showed you about after the PETM, there's that peak and it starts coming down. So here's the PETM, and we have this rapid cooling that takes off from there. The first Antarctic ice sheet shows up about 34 million years ago, and it is completely developed by 20 million years later. Once this happens and a couple of other things happen, it shoots us into our most recent ice age up here. Now, we don't exactly know how the glaciers first formed, like if we know exactly where they started. We have some great ice cores that show us where some old parts are. This is looking at 10 million years of glacier growth on Antarctica during this transition period. Probably these two right here. Well, these are 5 million year check marks, but this 10 million year point right here. So you start out with ice just forming in the high elevation areas. So if you were unfamiliar, Antarctica has a bunch of giant mountain ranges that we just see the tips of because it's covered in ice. It grows a little bit bigger, grows a little bit bigger, and then they finally connect, and boom, we have our ice sheet. So this is a model of how we think the ice might have grown on Antarctica. And one of the main reasons why the ice sheet grows in Antarctica is because around this time, Antarctica separates from everybody else. It becomes its own island continent. So for a very long time, Australia, India, Africa, and South America were all connected in one big giant landmass, and they start to break up. And I believe India shoots off about 50 million years ago, and I think the last connection points between Antarctica and Australia break away about 40 million years ago. What that does is allow Antarctica to move on to the South Pole. So remember, South Pole is a really good way to grow ice sheets. And the other thing is that it's not connected to anything anymore. And that forms the circumantarctic current. So there is a big current that just goes real fast around Antarctica. And that allows Antarctica to kind of hang out in its own climate. That current does a lot to keep Antarctica cool. So once that current starts to go around Antarctica, and it's on the South Pole, it's like a recipe for disaster. Well, disaster if you think ice is a disaster. So that's kind of the kickoff to the cooling of the Cenozoic. And what's that do on land? Well, we already saw that during the Eocene, it was warm. It was very warm still. And so this is what Wyoming would have looked like about 52 million years ago. This is the Green River Formation, if any of you are familiar. So we got the very first bats, got some crocodiles, got garfish, and the other little fishies that I don't know. And this is Uintatherium, a very weird early mammal, one of the largest mammals, if not the largest mammal during this time in North America. So it's swampy, it's wet, there's trees, you can see forests. But by the time we get to the Miocene, this is about 11.5 million years ago in Nebraska. It's totally different, right? I mean, we've got a little watering hole, but I'll tell you right now, this is like an oasis. There's no water coming in or out. This is a little pond that fills up and then dries out. So it's an ephemeral pond. This is ashfall fossil beds too, by the way. But we have horses and rhinos and these weird elephant things and bone-crushing dogs and cranes and giraffe-like camels, all sorts of weird stuff. And that kind of reminds you of a modern-day environment. Definitely not here in North America, but it should remind you of an African savanna, a wide grassland. So we had all these megafauna living in these widespread grasslands. I mean, where's the forest in this picture? There isn't one. We've got a couple of sparse trees, but mostly what has happened between the Eocene and the Miocene is it's cooled down, for one, and it's dried out. So all of those forests were replaced with grassland, which drove the evolution of mammals. We have this massive transition from mostly browsers that are eating leaves and shrubs to grazers that only eat grass. So as the grassland expands, the animals evolve with it. I'm just going to mention this one briefly because of ocean currents. About 3 million years ago, Central America connected. So for about 50 million years, South America was its own island continent. It did not touch anybody and nobody touched it. But about 3 million years ago, some volcanic uplift between two plates coming together uplifted what is now Panama. And animals that lived in North America went south, and animals that lived in South America went north. So this is the Great American Biotic Interchange. And the reason why I mentioned this is because think of the ocean currents. Before Panama, ocean currents could just, boom, go right through. It was easy peasy. Now Panama's here. Ocean currents coming from this way now get stuck and have to go all the way south. They get colder as they go south. They get deeper as they go south, and then they hit that polar current and get sucked up in there. So you get a whole different upwelling now, completely different upwelling. Same thing with anything coming this way. It gets hit and it has to go around South America. So it completely changed the ocean circulation, which then changed our climate too. Because this brings us to the Pleistocene Ice Age. About 1 million years after all of that happened with the Great Biotic Interchange, we start to get glaciers. So during this time, about 30% of Earth's surface was covered in ice. The ice sheets were about 1 to 2 miles thick, and it resulted in a temporary sea level drop of about 300 feet. That is massive. Can you imagine being in Puget Sound and the water is 300 feet away from you? And then the mean annual temperature at the edge of the ice, so like right here, was about 21 degrees Fahrenheit. And the edge of the permafrost that would go down a little bit lower was about 32 degrees Fahrenheit. So this was a very chilly time. But as to be expected, if you got 30% of your Earth's surface is covered in ice, it is probably pretty cold. So here's what it looks like in a climate cycle, though. So here's the Paleocene. Here is right about here-ish is when Panama forms. And you can see we go right into our cycles from there. And here's what I mean about how we hang out in a 41,000 year cycle, and then we randomly switch to the 100,000 year cycle. Again, this is still a big mystery, and we're not 100% sure what caused the main driver of climate change to change between the 41 and 100. But it changes quite a bit. So anytime the line goes down, it gets colder. Anytime it goes up, it gets warmer. So you have glacial, interglacial, glacial, interglacial. So we're technically still in an interglacial phase because we still have a polar ice cap. It's sitting on Antarctica. But it's getting warmer. Ah. Wrong button. Please start. Yes. Okay. Here in North America, I like this map mainly just because it shows you a little bit more what's going on beyond the ice. So we have Lake Bonneville. We have a whole bunch of glacial lakes up here. So in the southwest, there was huge lakes. So where the salt flats are today, some of the largest lakes that have ever been in North America. We have a nice, warm, temperate climate down here, like a boreal forest. So that's why Florida has all the great Pleistocene animals, because it was warm. You got sloths coming up from South America, terror birds coming up from South America, and living in this temperate, warm climate. So Montana in Florida. You got jack pine and tundra up here, spruce forests along the east coast. Manhattan, the island, would have been land, part of land. It wouldn't have been an island. But there's one thing missing on this map, and those are the glacial lakes at the front of the ice sheet. So, Glacial Lake Missoula. I'm just going to briefly talk about this. I did a whole talk about Ice Age of Montana, so if you want to check that out. But basically, same old story. Purcell Lobe comes down, blocks the Clark Fork River in Idaho, backs it up. The water goes to about 4,200 feet, the maximum depth of 2,000 feet. I should have all this memorized by now. It was covered an area about 3,000 square miles. The catastrophic failure released as much as 500 cubic miles of water at a rate of 10 times the combined flow of all present-day rivers combined. So if you want to see a really good example of what that amount of water does, go to the Camas Prairie ripple marks near Quinn's Hot Springs. And those are the largest ripple marks on our planet. And they were created by this catastrophic flood event. And this happened several times around 15,000 years ago. But again, if you want to know more about Montana Ice Age, check out my other talk. So now that brings us to our current situation. So here we are. This would have been Glacial Lake Missoula time right here. Starting about 15,000 years ago and somewhere into about the 12,000 years range, that's when agriculture starts for us, which we'll talk about here in a minute. But you can see our temperature thing has bobbed up and down. We're definitely in an interglacial time now. We've come out of a big ice age, and we're still in an interglacial cycle. This is the little ice ages down here. What's kind of fun about the little ice ages is that it might have been due to a massive decrease in human population from the Black Death and everybody in the Americas dying from colonization. So we might have actually caused a little ice age right there just by killing ourselves. Now, if we zoom in a little bit farther and look at from like 1890, 1850 to now, you can definitely see we are still trending up. So again, there's a difference between weather and climate. It can change drastically, we know, from day to day, but there's an overall trend in climate. And this trend in climate shows us going up. But now, what if we could take out humans from the equation? Would it still go up? So this graph is looking at the observed temperature, which is the black line, the human and natural drivers combined, which is the red line, and natural drivers only. So this is a thought experiment. This is basically taking data out of the model and seeing how the data runs. And what you can see here is if we take humans out of the equation completely, we're hanging out on that flat line that I just showed you. The big one that's looking farther out from the past 15,000 years. We'd be hanging out just right there. Now, when we add humans to the equation, you can see us humans track with the observed temperature. So we have definitely caused some massive change over this period of time. Now, there is a little bit of a lag between what we're doing and what we see. So the increases that we're seeing over here were probably from CO2 pumped out back here. So the CO2 that we're currently pumping out still has a little bit of lag time before it actually gets into our system and it actually does something. So we're still dealing with like last year's CO2 and it doesn't even count for this year yet. So that's also terrifying. Now this has caused a lot of people to want to give it a name, this period of time, and we've come up with the Anthropocene. Geologically significant conditions and processes that are profoundly altered by human activities, right? Well, we are having trouble with what to do with this word. It's a great word. I mean, humans love to name and categorize things, so why wouldn't we name an entire geologic time era after ourselves? But we can't decide what to do with it. So there's a group that wants to name it like a geological epoch. So that would be the same as Holocene. Right now, we're in Holocene. So if we made the Anthropocene epoch, it would end the Holocene and start the Anthropocene. Some people want to add Anthropocene as a subdivision, an age, underneath the Holocene. So it would still be Holocene epoch, but then it would be Pleistocene Age. Then there's a whole nother group that's like, this is too complicated. No, 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 no. Humans are not a point in time. We are an event. There is a lot of different changes that we have caused in a lot of different periods, in different places, at different times. And so these people want the Anthropocene to be more of an event like the Great Oxygenation Event. This would be the Anthropocene event, the human affecting event, but we wouldn't put it into the geologic time period. Now, if we do go with the geologic time period, okay, we want to add it to the geologic time period, we need a start date. That's really important for a geologic time scale. We need a start date. So when do you have it start? There's 3 options. One option is when we start agriculture. So a lot of times when humans want to make farmland, we tear down forests. And we've been doing that since the time immortal. So anytime we clear a lot of trees, you can see some climate change. And you can see that in ice cores. But ice cores are ephemeral. If we get hot enough to get rid of our ice cores, then we don't have the evidence of that climate change anymore. And we usually like more solid rock to say, okay, this one. The other one is the Industrial Revolution around 1800s. Okay, we start pumping out CO2 at a ridiculous rate. That sounds pretty good. Again, though, the evidence for that is in ice sheets. The one that would be more rock-driven is actually the start of the nuclear age. So when we start to test nuclear bombs, that's a whole bunch of radioactive fallout. And that fallout you can find still to this day. Levels of it, especially in the desert Southwest and the Bikini Atoll. They're still dealing with the effects of radiation. So that radiation spike all around the world will be there. So that's kind of where they're leaning right now, is the age of the nuclear era, either 1945 or 1963, depending on which test you want to go with. So those are the 3 time periods that we're leaning towards if we go to it to be part of our geologic timescale. Otherwise, this is just going to be known as the Anthropocene event, when humans messed everything up. And what's fun is if you think about maybe like what will be our fossil legacy? Distractium colossus, the remote is so funny. Cranium imperatrice for the climate denier. Oh yes, this one definitely. Proliferous absurdium. Yep. Yeah, I feel every single one of these, right? So now let's take the PETM. So that was our closest proxy to what we're doing right now. This is the depressing part of the talk. So here's the PETM. It was 2 billion metric tons of carbon per year. Oh, if only we could get down to 2 billion a year, right? This is what we're doing, 30 billion. When we look at the globe, this is present day in the 90s. I couldn't find one that matched. So the red, there would be red. If this was 2023, there would be red. This map has like 3 spots of red in South America. There would be a lot more than that. So there'd be some red, but otherwise we'd have a nice rainbow color here. Here's the PETM. That's very hot. This like pink color is up here. That's 36 degrees Celsius surface air temperature. So that's like 100 and some odd degrees surface temperature in those pink zones. So that's the PETM. Now let's compare that to some trajectory for the end of the century. Oh, look at that. They match. So the intense global warming that we saw during the PETM is bound to be repeated by the end of the century. And there's actually very little that we can do about that, because you might be thinking to yourself, well, hey, what was that whole Paris Agreement thing about, right? Like, that's supposed to save us all? No, it won't. So this is from a science article called A Roadmap to Rapid Decarbonization. And basically what they did is they broke down the Paris Agreement and put numbers behind it. A bunch of scientists were like, okay, you threw out a bunch of wish list stuff. Now what will it actually take for us to hit these, right? Okay, First one. Global CO2 emissions from energy and industry have to fall in half each decade. That is, in the 2020s, we missed that, right? The world cuts emissions by half. We sure did not do that. We went up in this last decade. So to even match Paris from 2017, by the 2020s, we were already supposed to half our CO2 production rate. Then we would do that again in the 30s. Whatever was left, we'd half that again. And then in the 2040s, whatever was left, we'd half that again. This is dubbed a carbon law, by the way. So we're already behind with that. Net emissions from land use, so agriculture, deforestation, those things, have to fall steadily to 0 by 2050. That means that we stop tearing down all the forests and we stop planting new crops by 2050. And this is all the while the world population grows and we have to feed more people. But we have to basically end all land use and get it to 0 by 2050. Oops, last one. Technologies that suck carbon dioxide out of the atmosphere have to start scaling up like absolutely massively. Until we're able to artificially pull 5 gigatons of CO2 per year out of the atmosphere by 2050. That's nearly double all of the world's trees and soils already do. So while politicians have hopes and dreams, they are very rarely backed by science. Vote scientists into government. Because that was our goal, to keep global warming below 2 degrees Celsius by the end of the century, right? And we have failed drastically already. I mean, the first one right off the bat. Instead of decreasing it even a little, we went up by a lot. So what's that mean for our total warming predictions? So we're going to be lucky if we end the century with only a 3 degree Celsius increase. If we do nothing and just, oh well, other people will worry about it, we'll go up about 5 degrees Celsius. So at least right now, with what we're doing, the little that we're doing, we will see probably about a 3 degree Celsius increase. So that's 1 degree over our mark. So technically we failed, but not too bad. If we hit our 2030 targets, which we're not, we're only like 7 years away from 2030, we're never gonna hit those, we would only go up by about 2.5 degrees. If all the hopes and dreams plus what we've already put into policy, we're looking at about a 2 degrees Celsius. The optimistic scenario here is everybody just tomorrow woke up and was like, let's change this. That's the optimistic one at 1.8. So this is where we're finally into what we wanted to do. But they're mostly hopes and dreams that aren't going to happen unless policy changes drastically, drastically. Everything about how we live right now would have to change for us to hit a lot of these. Now this one here is a super, super duper pipe dream that will never happen at 1.5. So these are our projections. This is what we're looking at. By the end of the century, it's going to be on average 3 degrees Celsius warmer. So that's like what? 12, 15 degrees Fahrenheit on average warmer. So we're already getting warmer here in Missoula on average. Can you imagine a summer where just the average degree temperature is 15 degrees warmer than it is now? Think of all the changes that we've seen. I mean, spring is basically a week now instead of a month. What happens if it gets 12 degrees hotter on average all year round? So there's some things that could happen if we look into our future Earth. So I'll leave you on a super depressed note, is that we're basically screwed. But let's look 100 years from now. This is from a book cover, actually. This is from a book by Kim Stanley Robinson. It's New York 2140. So this is a little over 100 years from now. It's definitely going to get warmer. You saw in our projections, no matter what we do, at minimum, it's going to get 1.5 degrees warmer, but probably closer to 3 degrees warmer. So the sea level is going to go up. And it's probably going to go up about 3 to 5 feet. Now, that's pretty manageable for most coastal communities. You're gonna have to build seawalls, you're gonna have to get all those Dutch things going, you're gonna have to do a lot. But it's not like Miami's gonna be wiped off the map. It's just gonna be a little soggy. It's gonna be Venice. And Venice is gonna be completely underwater. However, animals, depending on who you are not gonna do very well. So take polar bears. By 2140, there will probably not be any Arctic ice sheet anymore. And if you're an animal that only lives on ice sheets and you have no ice sheets, they're already interbreeding with brown bears and grizzlies, so their DNA won't be gone like Neanderthals, but they will be gone. Birds, it's gonna be rough for birds. It's already rough for birds. It's gonna get much worse for birds. So their migration paths are gonna change. Light pollution screws them up. The change in when things bloom, they're always kind of a generation behind. Amphibians, the fungal diseases are gonna get out of control. We'll be lucky if we actually have amphibians by the end of the century. Probably cane toads in Australia still, but everything else is gonna be gone. Reefs, obviously, are gonna tank hard. The biodiversity is gonna be outrageous. The corals are gonna bleach from acidification. It's gonna be bad. And insects are also gonna tank. We've seen a lot of them tank already, but there are some winners in here. Bark beetles, they're gonna do great. We'll be lucky if we still have our pine forests here in Montana by the end of the century. You've already seen how many we've lost just from pine beetles moving into environments that they're not supposed to be in because it's too warm. So think about if Montana never got below freezing, what that would do, because that's what we're looking at here. Now, when we look at the PETM and we think about parts per million of CO2, we still have alpine glaciers on Antarctica with 840 parts per million. That's 3 times industrial levels. So that's still pretty good. That's still ice on Antarctica. It stays fully glaciated at 560 parts per million. But our projected CO2 levels go from anywhere 400 parts per million. That's best case scenario with the Paris Agreement, which we've already seen we're failing terribly at. And the worst case scenario, an ultimate runaway positive greenhouse effect, is 1,400 parts per million. That would make Antarctica totally ice-free, and that would raise the sea levels by 80 meters. That coastal communities cannot deal with. So depending on where we go and how well we're to do, it may just be like this, where Manhattan is a little soggy, and you gotta take boats instead of taxis. Or this could be completely destroyed and underwater, and there is really no Florida anymore, or really East Coast. We'll be okay here, but we'll be a lot closer to the ocean. Now let's go a little farther. Let's think about the next 100,000 years. Does anybody know what this represents? No? Yes, it does. So within the next 100,000 years, Yellowstone will go off. This is the ash fall from Yellowstone. Right here in Missoula, we're gonna get if we survive it, we'll have a foot of ash. Now you may be thinking to yourself, well, hot damn, we survived. Let me tell you, volcanic ash is not to be trifled with. We have a foot of it. It clogs everything. Machines don't work, air conditioning doesn't work, heating doesn't work, your car doesn't turn on anymore. Animals suffocate and die, birds fall out of the sky. End of days with a foot of ash. I've seen what happens with ashfall fossil beds 11.5 million years ago when you get 5 feet of ash. And it just decimates. The whole landscape just looks like it snowed, only it's light gray ash. And if you look at volcanic ash under a microscope, it looks like little Christmas balls that have exploded. And then you breathe that in, and it just destroys your lungs. So I'm not sure how long we would last, but it's going to be rough. Also, all of this is going to go to the east because of the winds, right? Look how far it goes. That's Miami. Miami's still going to get 1 to 3 millimeters of ash. Guess what we do out here? This is where we grow a lot of our food. This is the bread basket and especially the grazing basket. look how much ash it gets. So it would basically completely cripple the United States if this goes off, when it goes off, and if there's a United States in 100,000 years, which I'm assuming there will be. But anyways, it's going to be trying times, to say the least. And that's if we get out of it without it going off tomorrow, because really it could happen at any time. We're overdue. We're very much overdue for Yellowstone. Not to freak you out anymore, but we're overdue for Yellowstone to go off. All right, let's go even farther. Let's go 1 million years into the future now. So the continents have shifted, but not by like a lot, no more than like 30 or 40 miles. So if you still looked at a 1 million year map from now, you'd be like, oh yeah, yes, all the continents are still, yep, I can see those. We would still have 24-hour days. We'd have a new Hawaiian island though. It's about 2 miles high right now. I think it's just like within like the last couple of years, it's like above the water now. But here it is. So it's gonna get bigger. This is the old name. And this is the new name that I'm not even going to try. I'm sorry, Hawaiians. I do not want to butcher it. But yeah, so we're going to have a new Hawaiian island. So mark your calendars. 100 times current human history has passed. So our current human history, multiply that by 100. That's where we're at. So that's a lot of human history to go. If we survive 1 million years, most species have an average time when they're around. And our longest human relative, Homo erectus, was around 1.3 million years. So if we want to look at our ancestors, we have a chance, for sure, to still be around as Homo sapiens in 1 million years. But the environment and how we have changed it and how it has changed over the 1 million years is unimaginable. I can't even begin to imagine what we have done to it and what it has done to us also. This goes 2 ways. But if we don't survive, if humans go extinct before this point of time, our geosphere and biosphere will return to pre-industrial equilibrium. It'll literally only take 1 million years to basically wipe all the stuff that we did to the planet away. So if that makes you sleep a little better at night, if we're gone in 1 million years, everything will reach homeostasis again without us. Let's go even farther. Why not? 50 million years. Earth is still going to be here. Like I said, we're not going to get enveloped by the sun until 10 billion years. So we got like plenty of time. Earth is still like a baby 50 million years from now. The fate of the human race is unknown. We will have definitely speciated by this time. Definitely. Unless we do something real weird that I can't even think of right now. Also, if we're extinct, if we go extinct at any point between these, especially like 1 million years ago, and it's been 50 million years without humans, almost every single trace of our existence will be gone. Yeah, we have fossils that are super old, but it's a tiny little fraction of what was actually alive during those times. So only a tiny little fraction of our entire existence will still be around 50 million years from now. We'll be gone, basically. Maybe we will colonize space. This is from a really fun book, Colonies in Space, that was written in 1977, and I'm totally going to buy a copy of it because the illustrations are amazing. So anyways, maybe we've colonized space. Maybe our Earth is a museum that we keep as a monument of our human evolution, where our species started. Maybe we've done some really great, amazing things. Maybe we're space pirates. Who knows? 50 million years from now. And one more, just for fun. 250 million years from now, all of our plates will come together in another supercontinent. Now, because we have no idea exactly what the plates will do, there are 4 current models of what this next supercontinent will look like. I will tell you, Amasia has the most support. But we already know that our current plates do some strange things that we cannot, the dog leg of Hawaii, for example. Nobody's 100% sure why it just was like, oh no, I'm gonna go this way now. So at any point in time, any of these plates could just change their direction. That's why looking into the future is so hard. But the reason why we know 250 million years from now we will have another supercontinent is because our supercontinent cycles go every 250 million years. Basically, since our planet has had land masses, every 250 million years, we have a different supercontinent. So 250 million years ago was Pangaea. So that's why a lot of these are like Pangaea Ultima, Novo-Pangaea, Amasia, America and Asia coming together. Eurica, Europe and Asia and America coming together. Anyways, they get fun with their names. But anyway, this is where we're headed to 250 million years into the future. By this time, we will have a little bit different day lengths. They'll be a little bit longer, not by a whole lot. There will be slightly more solar output, but like I said, it only goes up about 8% every billion years, so we're only a quarter of that. But yeah, that's where we could be in 250 million years from now. And with that, thank you so much. Anybody have any questions? Oh, I will leave you with this. If you ever do come up against a climate denier, I hope none of you in the room are, and if you are, I hope I might have changed your mind a little bit. And as you have seen, climate has changed a lot, a ton. That's not what anybody is arguing about. Anybody that understands climate change, nobody's arguing that with you. I know, it's done. We can see this. I just did an hour talk on it. The rate of change is what everybody is concerned about. And so if you ever run up against that, just be like, no, 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 climate change, yeah, yep, it does change. It's been super hot. We haven't had any ice sheets. It's been totally ice sheeted over. It's been a lot, over 4.5 billion years. But the rate of change right now is something that we have never seen in the rock record. We have 4.5 billion years of history, and we have never seen CO2 spikes like we're doing today. It's about 10 times faster than the PETM. We are in uncharted territory. We don't know what this type of input does to the system because it's never happened. We're playing a very dangerous game right now. But that's what I will tell you to fight the good fight with, is it's the rate of change that everybody is freaked out about, not that the climate is changing. Okay. Yeah?
This is kind of a strange question, but take, for example, the impact of the asteroid. Is there a possibility that the long-term, like if the asteroid, yeah, I guess I talk like
Well, we could talk a little bit about asteroids. So when we were trying to figure out why dinosaurs went extinct in the first part, there was a lot of very funny ideas. Some of you may remember those ideas, like they were too dumb to survive or stuff like that. Like we didn't really have a good idea. And then these father and son team, the Alvarezes, started poking around in Italy. And there is a boundary that seems to show the Kpg. And they got to poking around, and all of a sudden they found this layer, and it's about an inch or two thick, and it had incredibly high iridium layers. That was our first idea that there was something extraterrestrial that had to do with this extinction event. Now, all the critics were like, where's the crater? You can't have an Earth-ending asteroid impact and not have a crater. So then the hunt was on. We found a lot of them. We've actually have some bigger ones than the Chicxulub impact. None of them were the right time, and none of them seemed to be hooked up with an extinction event at all, for whatever reason. There was a geologist doing some work in the Gulf of Mexico, and they were using some ground-penetrating radar, totally separate projects, and they found a big crater. And the geologists were like, oh, that's just like a seamount. That's an old sea volcano. That's what that is, and just published it and went on business as usual. Well, a few years after that, somehow that paper popped up on a paleontologist's desk. And he was like, oh, wait a second. That's the right age. That's not a sea volcano. That is a crater. And so they went, took a bunch of tests, and drilled into it a whole bunch, and they matched that iridium layer that you can track almost anywhere that there's a Kpg layer around the Earth. You can find that iridium layer. And the closer you get to the Yucatan Peninsula, and to that crater, it gets thicker. So that's when we were finally able to be like, oh, okay. There's a couple of other things that happened with this impact that made it so much worse than all the other ones. One, it hit in the ocean, which you'd think that would make it better, but it didn't. It also slammed into a hydrocarbon-rich unit. So it was basically hit like an oil sand or oil and gas, a big like salt dome with like oil and gas underneath it. So you basically just threw gasoline on the fire. So that's kind of what made it even more worse, is that it hit in the absolute worst place that it could have hit. And so it basically just caught a whole bunch of oil and gas on fire on top of doing all of the other horrible things. If you want to hear more about how awful that impact was, watch one of my other videos. I talk very much in depth about that extinction event. Now, I didn't mention though, but I think by the next 50, yes, within the next 50 million years, we'll probably get hit by another meteor or asteroid that's at least as big as the one that killed the dinosaurs, unless we're still around and we have all sorts of sweet, like, asteroid defense systems and stuff that knock it off its course, like we're trying to figure out now. But we're due for another dinosaur killer asteroid within like 50 million years. They happen, you know, they happen. But again, we might be able to not get hit by it this time, which would change some things. Yeah?
I guess what my question is, all of these devastating things that happen to change climate, either cool it or warm it, our tendency is to try to stop that from happening. For example, an asteroid impact. You know, we're talking about blasting the asteroid away so it doesn't hit Earth. But the thing about all of these things, whether they're floods or volcanoes or asteroids, in a way they clean up our Earth and allow us to continue.
Oh yeah.
The asteroid brings in water and minerals and things like that. And volcanic eruption brings up all kinds of minerals that we...
Oh yeah, deep sea vents are just bio hotspots. Yes.
And in some ways too, it stops us in our tracks in these small areas. You know, it's not happening all over the Earth, which will...
Well, luckily, except for 5 times.
But it does stop some of our activities for a short time and maybe.
Humans have never... Yes and no. So, one, yes, there is a huge rebirth after extinction events. It's amazing what happens. Life has, whatever survives has just, the world is their oyster, right? There's all these fresh niches that they can move into, and anytime life starts to move into new areas, it starts to diversify. So you see these great flourishes of life after an extinction event. However, I'm not sure that I would consider that a cleanup, and I don't think the animals that lived during those extinction events would also consider them a cleanup either. Humans ourselves have never experienced a mass extinction event. There was a tiny little one at the end of the Ice Age that I don't mention with the megafauna extinction, so like we don't have mammoths anymore. There's a reason. But other than that, we really haven't experienced a mass slate cleaning and restarting event. Nothing has actually stopped us in our tracks at all, except for disease. Disease slows us down, but for the most part, we just deal with it and move on. Whoever survives has the immunity to keep going, type of thing.
Cleanup as a resetting.
Yeah, extinction events are a reset, for sure.
It allows the natural systems to start resetting themselves to the way our environment is, however it is, and to however all of these genetic things have gone to, instead of us. What I'm thinking is, if we keep trying to change the way it's evolving, we have such a limited view of what is happening that in some ways, these small extinctions, if we don't let it get to a big extinction, the learning is already in the system.
Yes and no. Yes and no. So here is where we should be. Here is where we are. So we have definitely changed this system. Is that good or bad? It depends on who you're looking at. If you're an animal that is all of a sudden available to move into new areas and new regions because it's getting warmer, so like snakes having a heyday, this is not bad for them. They do not see this as a bad thing. We have a very Anthropocene view of how cycles should work. But there's going to be winners and losers of every single extinction event. And us trying to get us back down to where we should be before we started screwing up everything is very unique to us. We have changed it, we see that change, and now we're trying to fix it. In no point has any life prior to us tried to fix the situation, to make it better for their homeostasis. But like I said, there's going to be winners and losers. There's always survivors of an extinction event. If you talk to them survivors, was that extinction bad for you? Heck no! Look at all this food and resources and space I have now that everybody else died. This was great for me. You talk to the things that went extinct, no, it was a really bad day. It's a really bad day. So I don't want you to think that a hothouse Earth naturally is a bad thing. These cycles happen constantly. Sometimes they're less extreme, sometimes they're extreme. But a snowball Earth is not any better than a hothouse Earth. It's not any better than an interglacial period. Yeah, it could be a little bit better for life, but who cares? So yes, it's getting hotter, but it's getting hotter because of what we're doing. So we need to recognize that and see, oh, when stuff gets really hot, it can be really bad for a lot of things. It can be good for things, but it can be really bad for a lot of things. And we have seen extinction events associated with really hot times. But those might not be bad. Like you said, it's kind of a reset. But it's not, I think it's getting bad, I'm going to reset it now type of like cognizant thing that happens. Except for us. Because we are environment, what's it called? Like tortoise. They shape their environment to fit themselves. Not a lot of animals can do that, to change the landscape to make it better for them. But we have been able to do that. And so that's what I mean, at least like wiping the slate clean, trying to change it from its trajectory. If we were trying to change it from its trajectory, we're changing it from an artificial trajectory. We're trying to get it down here. This would have been the normal trajectory. But this is the only time in our Earth's history where there's been an animal that has changed it that much, other than plants. Plants are the best thing that's ever happened to this planet and the worst thing that's ever happened to this planet at the same time. But I don't know if I'm answering your question. I'm not sure I understand your question. Anybody else have another question? Nuclear war would do about the same thing as the impact winter. And depending on mutually disturbed destruction, that could be really bad or it might not be very bad. Obviously, y'all lived during all the testing. You lived through, well, we lived through, but not a lot of other people lived through the bombings in Japan. So we know that society can handle a couple of nuclear bombs. It's just when somebody says go and everybody shoots them off. What's that tipping point that would take us into a nuclear winter? I'm not 100% sure, but we'd probably have to like let off quite a bit of our nuclear reserves, as well as other people with them. Yeah, that's why. De-arming would be really great, but that's not gonna happen. That's not gonna happen. But just one or two going off, locally destruction. Globally, meh. Other than anything that has changed in our DNA because of all of that radiation. But I'm pretty sure we got more radiation from Fukushima than we did from any of the atomic bomb testing. That was a horrible failure there. And that's also not adding into all of the other potential nuclear failures that we could have at other plants in the next 100 years too. So yeah, radiation is a kicker, especially when you can't get away from it. Like our ozone layer, hooray, thank you for that. But this is our own made here. Yeah, but it would be really similar. Mm-hmm. Yeah. Any other questions? I know. Come to my next talk. It's It's going to be a lot more fun.